In this problem, we're given a differential equation, and we're given two solutions. Now, having just learned about linear independence, it behooves us to check whether e to the negative 2t and its close neighbor e to the negative 3t are in fact linearly independent. They look similar, so are they actually linearly independent? Well, we can find that out fairly easily. If they are, then we can use them as our two elements of our solution. Well, we're going to find the Wronskian of e to the negative 2t and e to the negative 3t. And the Wronskian, again, is just the determinant of a matrix built out of the two functions in the first row. And in this case, t is our variable, so we build the second row by taking the derivative of each function. We'll get negative 2 e to the negative 2t, negative 3 e to the negative 3t, and then the determinant is that little diagonal minus diagonal product, e to the negative 2t times negative 3 negative 3t minus negative 2 e to the negative 2t times e to the negative 3t. We want to check whether this matrix is invertible, which means the determinant is not zero. So we're looking for not zero values. We can simplify this. All the exponentials turn into e to the negative 5t by the time we're done. We have a negative 3 here and a plus 2 e to the negative 5t here. And so we end up with negative e to the negative 5t, which is not equal to 0 for all x, actually. In which case, that means that this matrix here is invertible, so the only way to cancel out e to the negative 2t's and e to the negative 3t's is to have them multiply by 0, or we can simply say that these two functions here are linearly independent. All right. And as soon as we say that, then we have one solution, two solutions to the second order differential equation. Right away, we can go to the construction of the general solution. Make a new page here. So y, which is some constant times the first solution, e to the negative 2t, plus c2 e to the negative 3t, is the general solution. 2, our differential equation here, double prime plus 5 plus 6, 5y prime plus 6y equals 0. All right. Usually, especially after we get some experience, we won't go through the Wronskian demonstration every time, but it's this idea that we should see two linearly independent solutions that will come back up again, and even before the end of this week. So we'll take a look at a second example with the same idea, though. Let's first take a look at this differential equation here, which is a little more complicated. We've got 2x squared y double prime, 3x y prime minus y equals 0. Now, this only makes sense to talk about x being larger than 0 with our functions here. But aside from that, we should be able to verify the Wronskian of root x, which is, of course, x to the 1/2 in disguise, and x to the negative 1, which is 1 over x. These are two very different functions. Square roots and reciprocals look nothing alike, so we do expect these to be linearly independent, but we should verify it anyway just to get some practice. We simply write the functions out, build the second row by taking their derivatives, 1/2 x to the negative 1/2, and negative 1 over x squared will be that second row element. And then we take our determinant by the two diagonal products. We're going to get x to the 1/2 times negative 1 over x squared minus 1/2 x to the negative 1/2, that's 1 over x to the 1/2 down here, times 1 over x. And altogether, this is x to the negative 3/2 And this is also x to the negative 3 halves. At the end of the day, we have x to the negative 3 halves times, ironically, negative 3 halves. And that is not equal to 0, except at x equals 0, things are undefined, but that's not a problem because x is always positive. For x greater than 0, we're totally in business. Again, linear algebra logic, this determinant is not 0, meaning this matrix here for various values of x would be invertible, and so we have those unique solution ideas, but it means that x square rooted and 1 over x are in fact linearly independent. Having shown that our functions are linearly independent, we should actually show that they're solutions. So if we're asked specifically to show that these span the solution space, then we've shown that they're different, but we actually need to show they are solutions. So we'll do that on a fresh page. And our differential equation was 2x squared y double prime plus 3xy prime minus y equals 0. y1 is equal to x to the 1/2, or root x. And we're going to show it is a solution. How do we show it's a solution? As always, we do that by subbing in. And making sure that when we sub it in, we actually get the left-hand side and the right-hand side equal. Well, to do that, we of course need its derivative and its second derivative. So it's y1 with 2 derivatives. That'll give us negative 1/4 x to the negative 3 halves. All right. We take all these 3 and we sub them into our differential equation. We're going to get the following new left-hand side. So be clear here. This is our left-hand side of the differential equation. And 2x squared y double prime comes from here. Then we're going to add 3x and y prime, which will be 1/2 x to the negative 1/2. And last but not least, we're going to subtract a y, which is 8x to the 1/2. Now we don't say that's equal to 0, we're checking that it is equal to 0, but it should work itself out. We'll have negative 1/2 x to the 1/2, x to the negative 3 halves, x to the 1/2, plus 3 halves x to the negative 1/2 is x to the 1/2, minus 1 x to the 1/2, and sure enough we have negative 1 and negative 1/2, negative 3 halves, plus 3 halves, that equals 0, which is equal to the right-hand side. So y1, which is root x, is a solution to the original differential equation. Similarly, we can look at y2, which was x to the negative 1. Going back one page, these were our 2 proposed solutions. We're just going to verify them. Of course, we need to show it as a solution by summing it in. To do that, we need to find its derivatives. That's y2 prime, and then y2 double prime. Take another derivative, we'll get positive 2x to the negative 3. Take these and sub them into the differential equation. Our left-hand side becomes 2x squared times y2 double prime plus 3x y prime plus, minus the y value, which is, this solution is x to the negative 1. So we get our left-hand side equals all of this. And if we start canceling, we're going to have 4 x to the negative 1s, and we're going to have 3 x to the negative 1s minus an x to the negative 1. Oh, wait a minute. Oh, careful. Negative 3. So that becomes negative. And phew, that was a good check, because now we have 4 minus 3 minus 1. That's 0, x to the negative 1s. That equals our right-hand side, check. And so y2 is equal to 1 over x is another solution. So what we verified is that root x is one solution, one function I can plug in and have it satisfy the differential equation. y2 equals 1 over x is also something that we can plug in and verify it's a solution. Going back, we've shown that those two functions, root x and 1 over x, are linearly independent. So we put it all together, and now it just becomes trivial to ask, or answer rather, what is the general solution to exactly this equation? Well, we know that y is equal to some constant times root x plus some other constant times 1 over x is the general solution. Right away, our two solutions with arbitrary constants in front are also going to be solutions because the equation is linear in y. And that's our gift, is knowing that the linear independence and that they're both solutions, we can instantly get the set of all possible solutions.